Welcome to the fascinating world of quantum superposition. This principle, as counterintuitive as it may sound, is at the heart of quantum physics. It suggests that any quantum particle can exist in all of its theoretically possible states at once. Yes, you heard it right, all states all at once, until we measure it, that is. Picture this, a coin spinning in midair. While it's in motion, it's neither heads nor tails, but both. It's only when it lands, when we observe it, that it takes on a definite state. This is essentially the concept of quantum superposition, but on a much smaller scale. Now let's dive deeper. Recently, theoretical physicists from the University of Innsbruck have proposed an intriguing experiment. They're aiming to generate a macroscopic quantum superposition state. That's right, a quantum state that's not just confined to the microscopic world of particles, but one that could be observed on a larger scale. The physicists propose using an optically levitated nanoparticle and cooling it to its ground state. Then they plan to evolve it in a non-optical potential created by electrostatic or magnetic forces. The goal? To overcome the hurdles of heating and decoherence that occur when using laser light. This approach, as ambitious as it is, could potentially meet the necessary criteria for preparing macroscopic quantum superposition states. The team is now working with experimental partners to put their theory to the test. So, could we possibly see quantum effects at a larger, more noticeable scale? Stay tuned to discover what these physicists have in mind. The physicists from the University of Innsbruck have a plan, and it involves nanoparticles and a whole lot of cooling. This plan is not a scheme to combat global warming, but a radical approach to tackle one of the most intriguing phenomena of quantum physics, superposition. Imagine, if you will, a nanoparticle, a tiny speck so small it's hard to comprehend. The physicists propose using an optically levitated nanoparticle, a particle suspended in space, not by magic, but by the power of light. This nanoparticle is then cooled to its ground state, the lowest energy state it can be in. No, it's not a nanoparticle on an ice bath, but one stripped of all excess energy, ready to reveal the mysteries of quantum superposition. The next step in the experiment is where things get interesting. The nanoparticle, now in its ground state, is evolved in a non-optical potential. This simply means that the nanoparticle is manipulated using forces that are not light-based. This is a significant departure from conventional methods, which typically involve laser light. But why this switch to electrostatic or magnetic forces? The reason lies in the inherent limitations of laser light. While lasers have been instrumental in quantum experiments, they also bring with them challenges of heating and decoherence. In simpler terms, laser light can cause the nanoparticle to heat up and lose its quantum state, making it harder to observe quantum superposition. By using electrostatic or magnetic forces, the physicists hope to sidestep these issues. Furthermore, the absence of light might even allow for these quantum effects to be observed in a more macroscopic scale, bringing us one step closer to bridging the gap between the quantum and the classical worlds. Could this new approach be the key to overcoming the challenges of heating and decoherence? Only time will tell. In the meantime, we can marvel at the ingenuity and audacity of these physicists, who continue to push the boundaries of our understanding of the quantum world. This isn't just an experiment for the sake of science. The results could have far-reaching implications. Imagine, if you will, a world where we can successfully generate a macroscopic quantum superposition state. This isn't just about producing a fancy physics term for a trivia night. This could fundamentally alter our understanding of quantum physics. You see, quantum physics is a realm where things can exist in multiple states at once, thanks to the principle of superposition. A particle can be here and there, spinning this way and that way, all at the same time. But this strange quantum behavior has so far been limited to the microscopic world, the world of atoms and particles. Now, what if we can bring this quantum weirdness to the macroscopic world, our everyday world? This is what generating a macroscopic quantum superposition state means. It's like saying an object can be here and there at the same time in our perceivable reality. It's a mind-boggling concept, isn't it? But it's not just about changing our perception of reality. If achieved, this could have practical implications too. It could potentially pave the way for new technological advancements. Think about quantum computers that could solve complex problems in seconds, which would take conventional computers thousands of years to solve. Or quantum teleportation, which could revolutionize the way we travel. Remember, these are just possibilities. But they are possibilities born out of the fascinating world of quantum physics, a world that continues to surprise us and challenge our understanding of reality. The world of quantum physics is as mysterious as it is fascinating. Who knows what amazing discoveries await us in the future? We've delved into the complexities of quantum superposition, explored a groundbreaking experiment, and pondered the potential implications. But what does it all mean? Well, let's take a moment to tie all these threads together, shall we? We started by taking a deep dive into quantum superposition, a mind-bending principle where a quantum system can exist in multiple states simultaneously. We then turned our attention to an experimental approach proposed by the brilliant minds at the University of Innsbruck, aimed at generating a macroscopic quantum superposition state. This approach revolves around an optically levitated nanoparticle cooled to its ground state and evolving in a non-optical potential. What's remarkable about this approach is how it seeks to overcome the limitations of heating and decoherence, the insidious effects that have long been the Achilles heel of quantum experiments. By shifting away from using laser light and instead employing electrostatic or magnetic forces, the researchers believe they can create a more stable environment for observing quantum phenomena. But why does all this matter? Well, these advancements open up new possibilities for understanding the world around us. The successful implementation of this experiment could potentially give us a clearer look into the strange world of quantum physics, providing us with valuable insights that could revolutionize everything from computing to medicine. However, it's important to remember that this is still an ongoing journey. Quantum physics, like any field of scientific inquiry, is marked by constant evolution and refinement. Each new experiment, each new discovery builds upon the last, propelling us further into the vast unknown. Quantum physics continues to challenge our understanding of the universe, and this experiment is just another step in our journey of discovery. As we continue to push the boundaries of what we know, one thing is certain: the world of quantum physics is full of surprises.